Namaskar. So let's see in this lecture about the whole summary of the chapter about current electricity. So here we will discuss briefly that what we have learned, and there will be some key points which you should remember, and also you should make your own key points when you are completing your chapter or while studying, because that is very helpful during your examination when you don't get time much to revise, but with this you can quickly revise all the concept and you will remember everything. So here we'll discuss that, and also we'll solve some very selected problems, and after that you can also try to solve more and more numerical problems related to this chapter, and that will be very helpful in understanding the concept and how to utilize it in application. That's really useful. So let's begin. So very first thing which we had discussed about is that electric current. So what was the electric current? Electric current, if let's say this is the cross section through which there is a conductor, and this is the conductor, and this is the cross section through which the number of electrons, the free electrons are moving, the charge is moving, you can say. And let's say with this given point of time that this cross section in delta t time, this is the total charge crossing this point in delta t time, then you can give the current is delta q by delta t, and also you provide that delta t is tending to 0, right? So it would mean that you can also write as dq by dt in the other terms, and the unit of current is given as ampere, right? Ampere. So you represent it as A. So 1 ampere is equal to 1 coulomb per second. We had also seen about current density. So what was current density? So let's say if this is a conductor and this is your some normal cross section area, and then this is the current flowing through it. So then current density is defined as vector J, which will be equal to this is the di current flowing through it, so it will be di by dA, right? So this is the current per unit area flowing through a conductor, and in this other terms you can write J is equal to vector J dot D, dot product of the area. So it would mean that if you want to determine the total current flowing, if you have this current density known and that cross sectional area, for example in most of the wires you get the cross sectional area, and if you know the current density, then you can calculate what would be the current flowing through it, and that would be vector J dot dA product, and you can integrate it. So generally you can get dot product. It means that vector D, the J dA cos theta, right? So important point that current is a scalar, and current density is a vector quantity, right? It's a vector because it have direction, because it is associated with the cross sectional area. So what angle it makes, that will define that what meaning current is flowing in a given direction. Also talking about that, in a current we also talk about the direction current whenever we are talking circuit. For example, in Kirchhoff law we had seen. So the current is generally taken as that when the direction of positive charge flow. So if the positive charge is flowing in this direction, it only means that in most of the conductors we are talking about free electrons. So the electrons flow, it is opposite the electron flow direction. So it means the electrons are flowing in this direction, then the current in the circuit will be in this direction, right? So that's a very important aspect you should remember. The other term we had seen about drift velocity. So drift velocity is that the average velocity with which electrons moving towards the positive end of the conductor under the influence of external electric field. So let's say this is the electrons, this is the electric field, right? So the electrons will be moving there in direction. So the direction with which the charge is flowing in the direction of electric field, that is given as drift velocity, and generally it is given as you have seen that it is E upon m tau, where tau is the relaxation time, right? And mass of electron, E is the electric field. So we define the current in terms of drift velocity I, which is written as NE capital AVD, where A is the cross-sectional area through which the current is flowing and the charge is flowing, and number of charge per unit volume, electric charge value, and the drift velocity. So from here you can also find that the current density can be given by I by A, and it would be NEVD, right? We had also seen a term called mobility. What is mobility? It is defined as drift velocity of the per unit electric field for a given charge. So mu is written as drift velocity of the charge per unit electric field. So it can be written as E tau by m. If you are following the this equation, then you can just get that this equation from that. We had discussed about Ohm's law. So what is Ohm's law? So if there is a conductor and between these two ends of the conductor, so there is a potential difference V, and the I current is flowing through it, then it is found that V is proportional to I, and generally it gives a constant called resistivity of the material. So and this is known as also Ohm's law. One important point of Ohm's law, like if a material having not following V proportional to I, it will still be valid to use V is equal to Ri there. It is Ri is not Ohm's law is not a fundamental law. It is just the consequence of this proportionality, if it is following or not. But if it is following, then it will be the resistance terms. Otherwise, it will be some modification to that. So it would mean that you can still apply to the materials which don't follow Ohm's law. This equation is still valid because this is the fundamental equation. So it would mean, it simply means that the materials which are following Ohm's law, which have proportional to I, it would mean that the resistance is independent of the voltage difference between these two, right? This is just that significant point with the Ohm's law. And I discuss this is known as resistance, and it is given as represented as R, and the unit is given as in ohms with his name, and this is the symbol, Greek symbol for representing it. And we had also seen that it also depends upon the geometry of the material. So for example, if R is given as rho L by A, where L is the length of the conductor, area is the cross-section area of the conductor, and rho is the resistivity of the material. And we had seen that how resistivity depends. It is 1 upon sigma, and we had also seen that J is equal to sigma E, where we had derived the point sigma was equal to n square tau by m, right? So from there you can find your what would be rho. It would be inverse of it. So some important units related to that. So you have a resistance. The unit of resistance is written as ohm. We represent it like this, and you have a resistivity. Resistivity unit is ohm meter, and written as ohm dash meter. And you can written conductance, that is defined as 1 upon R, reverse of the resistance, and it is written as mho, or also written as ohm inverse. And the other thing is that current density. So what is the unit of current density? Ampere per meter square. We had also seen about carbon resistors, right? Carbon resistor, which is very compact and very useful in many electronic devices, you can see. So it will look something like this, right? You have some small compact with some wire coming out, and it have colorful strips, right? And we have a fourth strip which just gives the tolerance of it. And the acronym which we had followed to remember is that, if you remember, it is BB ROY of G is just to remember great, you can write blue is written as Britain, violet is written as very, grey is written as good, and white is written as wise, right? So it is black, brown, red, orange, yellow, green, blue, violet, grey, and white is white, right? And the numbering you can follow 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and for the case of the multiplier, it is 10 power 0, 10 power 1. Similarly, you can go up to 10 power 9, right? Also, we had this this color, the tolerance color. The gold, if it is gold, then it was 5% tolerance. If it is silver, then it have 10% tolerance, and if it have no color, then it would mean 20% tolerance, right? And just to remember again, BB Roy of Great Britain here had very good wife, right? Black, brown, red, orange, yellow, green, blue, violet, grey, white. Okay, all right. Now we had seen about combination of register, where we had discussed that series connection, parallel connection. In series, you have the connection connected like this, right? We have only one end is connected, and in this case the resultant was given R equivalent is equal to R1, R2, R3, and so on till at n registers. Similarly, for parallel, you had both ends of the register connected together. So let's say these are the registers, and you can have so many registers, and they are all connected to one end connected to one point, the other end to other point, right? These are, let's say, a point AB, and this is R1, R2, R3, and so on, Rn. And then in this case you can have the inverses of R equivalent, it can be inverses of different registers, right? So you can have 1 upon Rn. We have seen Kirchhoff 2 rules, right? What was that? First rule was junction rule, that at any point the incoming current is equal to sum of outgoing current, and that in a closed loop the change in the potential is the observing sum is 0, right? So these are the two basic law about Kirchhoff law, and also the signal which you had followed. If you are going, this is your path following in the loop, and if you are register entering in the current direction in this, then it will be given as, if it is R, it is minus R, and if this is the, and if it is opposite, then it is plus R. And similarly, if you are entering in a cell from path is this, and if you are entering in a cell in this path to in minus and emerging out from positive in the path which you are following, then it will be given as plus epsilon, otherwise it will be given negative. So that's very important you remember. We had also seen about Wheatstone bridge, right? We had this kind of combination which each has a cell arm, right? We are having this kind of connection, and here we had a galvanometer, and this was Ig if it is made 0, and then it is the Wheatstone combination. If it is R1, R2, R3, R4, then you have the relation R2 by R1 is equal to R4 by R3, right? Also, we had seen about potentiometer, which is generally used to devise the potential differential between the two electrodes, and we had seen how to determine, compare EMFs, and internal resistance for the cell. Okay, so this is not it. You can make a lot, you go through it again, you make your own note. I have just given you a highlight how you can utilize this. And now moving further, let's solve some few problems which will be now we have run the theory. Now how the problems look like that, it will really test your concept, and the problems can be made where, so if you have a better understanding of the concept, then you can obviously solve the problem, but you practice more, that would be very useful. So let's see. So this says that suppose the drift velocity is a material varied by applied electric field like Vd is proportional to E, then what would be the IV graph look like out of these options? So as we have seen that what is the current, we are talking about VI curve, right? So we need to know that what is the current dependence on Vd. So as we have seen, it is NEA Vd, right? Now it says that Vd is proportional to E. It would mean that Vd is proportional to V because E is proportional to V, right? So it would mean that if you utilize this equation and this equation, then you can say that I is proportional to V. So if I plot the curve, then it would be something like that. Proportionally it would be moving and it would have a straight line of curve. So this would be correct, but assume that if it would have been Vd is proportional to root E, right? It can be given anything, then, right? This is just a problem. You can vary it and make 1,000 different problems from the same. So let's say if this is there, then what would have been? Then you would have got in this case the dependence of this is root E. It would mean that the Vd square is proportional to E, right? So if following the same analogy here, and I could have given I square is proportional to V, right? So in this case it would have been this curve, right? So this is for root E, and this is for Vd is proportional to E, and this is for Vd proportional to root E. So that's important. You understand the concept, don't remember the question. Even sometimes people remember the question and they don't think the changes in that, and then just tick the old remembered answer, and that's a very big mistake you people do. So you don't do that. Now moving next, and let's say this problem says that find the a bulb is rated with this rating to 220 volt 100 watt. Now we need to find the power if I am operating it as 110 volts. So how much power it will consume. So that's really very important and very nice question. So here what we can get information from here. So in both cases, the bulb resistance is going to be common because this is the property of that bulb. So from here you can find the resistance. So what would be the resistance? You can have V square upon P as P square V square upon R you can utilize because we are given power and voltage, and then we can get the resistance from this, and that would be somewhere 220 square upon 100, let's say. Now we want to calculate now that what would be power at 100 volts. So now we are given 110 volt, and then we need to find out what would be the power, right? And here we know the resistance from here, so you put this here 100 and you solve it, you will get what you will get. Oh sorry, here it will be here P is equal to V square upon R, right? So here you need to calculate power, so you will get 110 square, and R you calculated here, so it is 220 square by 100. So 100 will go up, and this you can take 4 out. It will be 100 by 4, and it would mean that it will consume 225 volt. Right, now you see that the rated, you just utilize the concept, find the resistance, and that resistance you find the file if it is operating at different voltage. So these are some very good examples you should try, and also solve more and more problems I would suggest, because there you will get more clarity on the concept and the missing links should be added there. So just try to solve, and it is also helpful for your exam and many other competitive exams you are proceeding further. So this is all about this chapter. So we'll end this chapter here and see you in next chapter from the next lecture. So thank you.